All right, so it is 10 o'clock and we will get started. So let me share this PowerPoint. All right, so just as a reminder of what we did on Wednesday, we started to look at precipitation reactions where you mix two substances that are soluble and they make a new substance that's insoluble. We learned how to read this table and figure out what substance is soluble and which one's not soluble. Then we looked at complete ionic equations and net ionic equations, where your complete ionic equation is all the ions present in a reaction. So you take anything that's aqueous and you break it apart into its individual molecules. And then the net ionic equation gets rid of any spectator ions. So a spectator ion is an ion that appears on both sides of the equation, because the spectator ion isn't actually doing any chemistry, it's spectating. So when we do the net, we want to talk about what changes only. So now we're going to continue on with our discussion of solution chemistry and go into a brief overview of acid-base reactions. All right, so first we have to talk about what is an acid, what's a base. And there's actually a couple definitions. For right now, we're just going to stick with what's called the Arrhenius definition. And the Arrhenius definition says that an acid will produce an H plus molecule in water. Now, for just complete clarity, H plus doesn't actually exist. What happens is that an acid will give an H plus to water to make H3O plus. This H3O plus is called a hydronium ion. So that's what an acid does. It creates hydronium ions. While what a base does is that it produces these hydroxide molecules in water. So a base will break down to create OH minus. So that's what a base is, produces OH minus in water. And when you mix an acid and a base together, what you create is water and salt. So that's why, like, if you spill an acid, what you're supposed to do is pour a base on it, because the acid and base will neutralize each other and the resulting mixture will just be salt water. Here I have an equation where we have hydrofluoric acid, so that's our acid. And we generally know it's an acid if there's a hydrogen in front. There are a lot of cases where the hydrogen isn't in front and it still can be an acid. But if we come across a molecule with a hydrogen in front, we're pretty confident that's an acid. So we have an acid plus our base. Anything that's just OH, that's going to be your clue that that molecule is a base. So you see anything OH, metal plus OH, that thing's a base. And what happens is that you form H2O. So the hydrogen and the OH will react together. And what you're left over with is sodium fluoride, a salt, NaF. If we look at the complete ionic equation for this, we can break that down and then get rid of our spectator ions. And our net ionic equation is simply H plus OH minus makes water, right? Now, we have different types of acids. What we looked at in our example there is just an acid that has one acidic hydrogen, but other acids can release more than one H plus. These are called polyprotic acids. Poly means many. Protic simply means like proton. So many proton acid, polyprotic acid. Sulfuric acid, H2SO4, is diprotic, has two hydrogens that are acidic. H3PO4 is triprotic. It has three hydrogens that are acidic. Now, some terminology for us, and I know it's cut off, so I'm going to rewrite it. Right? So we have another example down here where we have OH, which is going to be our base, and HCl, which is going to be our acid. So if we mix these two together, what we're going to form is water and chlorine. Now, this is a topic that will come up more in Gen Chem 2, but I'm going to introduce it here. It's these ideas of conjugate pairs, right? So a base in an acid-base reaction, so if we have OH minus, which is our base, and it forms H2O, the way we call these are a base will always form a conjugate acid, right? These are called conjugate pairs. And when you have a base in a reaction, it forms an acid. H2O can act like an acid and reform OH minus. So that's why they're conjugate pairs. A base will form an acid. While HCl, when it goes in a reaction, it will create Cl minus. So you have your acid and your conjugate base. Because Cl minus could act like a base and get an H plus from water and reform hydrochloric acid. So just keep that in mind. An acid in a reaction will form a conjugate base. A base in a reaction will form a conjugate acid. When you're looking at these groups, they're called conjugate pairs. And the only difference between molecules and the conjugate pair is exactly one hydrogen. That's the only difference, one hydrogen. Any questions about all that information? I know that's a lot of information to start your Friday, so any questions about that? Mind blown? Yeah. Acids and bases are, there's a lot of stuff to go with acids and bases. Acid turns into a conjugate base, as shown right there. It loses its proton and creates a base. We call that a conjugate base. A base gains a proton, and we call that a conjugate acid. All right. So let me clear this. So I know that's a lot to take in, but let's see how we're going to use this information now in practical applications. All right. So the first thing we need to be able to do is we need to look at an acid and a base and just write a balanced molecular equation for it. So what I'm going to do is I'm actually going to do B, because A is testing your knowledge. Actually, I'll just do A. I was going to say it's testing your knowledge on names of molecules, but I'll just do A. So what we need to do is first figure out how acids and bases react in a molecular equation. So we have hydrobromic acid. So this is throwing back to test 1. So like I've been saying, if you don't understand something from the previous material, you might be lost moving forward. So we have hydrobromic acid plus potassium hydroxide, so KOH. And what I expect people to be able to do for test 2 is 1, figure out when an acid and a base react, what are they going to make? And the answer to that is salt water. So you take your hydrogen from your acid plus your OH from your base, you make H2O. And let's just take a minute to talk about symbols. H2O, if it's liquid, always gets the L form for liquid. H2O is not aqueous because you cannot dissolve water in itself because it is water. So it can't be aqueous, which means it's liquid. So water gives the liquid, the L notation. All right. So we have liquid, and then we have the leftover salts. Potassium, bromide, aqueous. So that's what I expect us to do first. Figure out the balanced molecular equation, and this is balance. 2, when we look at an acid and base, do the net ionic equation like we did on Wednesday. So here's net. You just break up anything that's aqueous. Make sure you give it charges. So hydrogen is always +1, aqueous. Plus bromine, bromine's always -1, aqueous. Plus potassium, potassium's always +1, aqueous. Plus hydroxide. Here's a common mistake I see all the time. Do not break up OH. OH does not break apart. Are acids always aqueous? Yes. In this class, acids will always be aqueous. It's possible there will be a solid. You can have acids in the solid form, but we probably won't see that. And I mean, acids can be in any form now I think about it. Acids can be a gas. Acids can be a liquid, but in this class are going to be aqueous. When naming an element, which takes priority? The metal always goes first. So when naming an ionic compound, it's always metal, non-metal. So it would be potassium bromide, not bromide potassium. Doesn't matter which one comes first, K or Br. Yeah, so similar question there. Again, yes, it does matter in that you will never see BRK. I probably, at this point, would not care as long as you got the idea, but metal goes first. What is the charge of OH? OH is always -1. So hydroxide, -1. Then we do not break up liquids or solids, so H2O stays a liquid. Plus, then we break up potassium and bromide. So that's our net ionic equation. Any priority for 2 nonmetals? Carbon goes first usually, but that's usually based on how they're bonded. So you generally need to know the Lewis structure to get priority for how to name nonmetals in a covalent compound. And so we'll look more at that like in November. So kind of, but don't worry about that right now. All right, so there's our net. Sorry, that's not our net. That's our complete. That's our complete. I was going to say, like, where do we go from here? That's our complete ionic equation. So our net is we simply cancel out everything that's the same on the both sides of the equation. So hydrogen cancels out. No, hydrogen does not cancel out. What am I talking about? It's Friday, people. Bromine cancels out because it's the same on both sides of the equation. Potassium cancels out because it's the same on both sides of the equation. What we're left with is hydrogen plus OH minus, don't forget the state symbols, make water. All right. So C, if you can do that for B and then C, while I look at these questions here, Yeah, that would be our complete set of the net. But yeah, see if you can follow that notation and do the same thing for B. And I'm gonna give you a hint right now. I know you're gonna be tempted to do this, some of you. When you see polyatomic anions, do not break apart. I know I wrote donut, but do not break apart your polyatomic anions. SO4 stays together because they are covalently bonded. So you're going to be tempted. I see it every test, but do not break that SO4 apart. All right. If you have questions, let me know. Otherwise, I'll give everybody a few minutes to struggle through this. Remember, this pain that you feel is making you stronger. What are they saying in a gym? No pain, no gain. Same in the classroom. If your mind's not hurting, you're not trying. So let's see if we can get through this. Yeah, if you have a question or if you're stuck, don't hesitate to reach out. Yeah, I was going to say if you're stuck, if you could give me a little more information than I'm stuck, that would be great too. I know it's hard because usually in a classroom I would see what you're actually doing on paper and I can't. What would the salt be the salt form from B? Does anyone know that? I'll leave that up to the class. It would involve sulfate and calcium, yes. So calcium's a metal. Sulfur and oxygen are nonmetals. So you have a metal and a polyatomic nonmetal that makes a salt. Yes, anything on the left-hand side of the periodic table, calcium's in column 2, is a metal. Just as a reminder, so if you look on the periodic table, by aluminum, you should see like a dark line that zigzags. Anything that touches that line is a semi-metal. Anything like to the left of that line is a metal. Anything to the right of that line is a non-metal. All right, so let me clear some of my scribblings here. So let's take a look at this. Sulfuric acid plus calcium hydroxide makes what? Okay, so we have an acid and a base. We always make water, so H2O. And we also make a salt. Our salt is going to be calcium sulfate, aqueous. Now we have to make sure this is balanced, and it's currently not. We have 4 hydrogens on the left, 2 on the right, and so if we put a 2, that will actually just balance our equation for us, right? So you take your water, you make your water, and then you combine your metal and your non-metal to make your salt. So that is our balanced molecular equation. So let's do complete. Even though I don't ask you for the complete, I just ask you for the net. Let's do complete here. Yep, that's how you make your water. So complete. And I will say on tests, I have seen people be like, well, is it H40? No, water is always H2O, unfortunately. We cannot have H40. So our complete ionic equation is we have 2 hydrogens. So hydrogen will never be H2 in solution. It's always just H by itself. So don't make the mistake of doing H2, H3. It's always H. And you might want to make a note of that because I see that all the time too. If you are tempted to do H2, that's not correct for this. H2 does exist, and we'll talk about that later. But right now, it's just H plus SO4 minus 2. All right, here's a question that I usually get. How do I know it's minus 2? Reason 1. You remember on test 1, I gave you that list of polyatomic ions and told you to memorize it? This is one of the reasons I told you to memorize it, because we use these polyatomic ions all the time in general chemistry. And if you would have memorized it, you would have remembered SO4 is minus 2. Point 2, how do I know that? Let's say that you didn't memorize it or you don't remember. Well, if you remember, hydrogen is always +1, and I would commit that to memory. That's super useful. Hydrogen always has a +1 charge. I have 2 hydrogens. So to create a molecule that's neutral, I need something that's overall a -2 charge. So SO4 must be -2. Okay, so we have that. So aqueous, let's not forget our signs. And calcium's +2. Second column, metal. Like I said, any metal that's in the second column except barium will be +2 always. +2 OH minus, aqueous. Again, OH is always a -1. That's something I would commit to memory too. That's always -1. Do not do OH2. That is not correct. That 2 is saying you have 2 copies of this molecule. All right. And what we make, oh, this undo takes forever. What we make is water plus calcium 2 plus SO4 2 minus. Yeah, so there's your complete, your net. I'm gonna just cancel out spectators here. And your net is 2H plus aqueous plus 2OH minus aqueous makes, I forgot the 2 there, 2H2O liquid. What would be the charge of section 3B through 2B? I think, are you talking about like on the periodic table, 3B? So anything that's not in column 1 or column 2, or anything that's not a halogen or oxygen, those charges change, so we don't know. I cannot tell you, like, with the exception of like aluminum, zinc, and something else that's escaping my mind right now because I don't have my periodic table in front of me because I'm not a good student. Most atoms we do not know the charge of, so we have to rely on what we do know the charge of. And we're going to look at this probably not today, even though that was today's plan when we look at oxidation states. But like iron, I can't tell you what the charge is because the charge changes. Copper, I can't tell you what the charge is. The charge changes. I can only tell you column 1 is always +1. Column 2 is always +2. Halogens, -1. Oxygen, -2. Aluminum, +3. Zinc, +2. Silver, +1. That's what I can tell you with confidence. Okay. Next one, hydrochloric acid plus barium hydroxide. Well, that makes water, and that makes barium chloride. Here's another question I'm sure you're wondering. How do I know it's BaCl2? All right, so halogens. Cl's a halogen. Halogens are always -1. Barium is in the second column, but barium can actually have multiple charges. So how do I figure out the charge of barium? OH is always -1. I have 2 copies of OH. So to have this be a neutral molecule, barium has to be +2. So if I want to make a neutral compound of my salt, I need 2 versions of chlorine or 2 copies of chlorine to go with barium. The liquid here. Aqueous here, put a 2 in front of there, 2 in front of there, that should be balanced. Again, I'm not walking through like as in depth of how we balance stuff since we've already done that, so I'm going to be doing it rather quick. Moving on now. All right, so that's our equation, complete. Break everything up. 2H plus, 2Cl minus. Barium, 2OH. Again, OH is a unit. Do not break up OH. 2H2O liquid plus barium plus 2Cl minus. Aqueous. Aqueous. Net. Cancel out all the spectators. And this should not be a surprise at this point, hopefully. What you're going to have left is water interacting. So in acid and base, what are you doing? You're making water. So hydrogen, 2 hydrogens, sure, we can keep red, plus 2 OHs makes H2O, 2. Liquid, ake. Easy peasy, right? All right, questions about that? Where did I lose people? Why won't my pen switch back to black? There we go. No questions? Clear as mud? All right. Then I'm going to clear this nonsense. Oh, that wasn't a pen. That was annotations. That's why it was different. Well, I'm guessing that's going to stay there. So, oh well. All right. The last thing we're probably going to talk about, and something you're going to be doing in the lab if you haven't yet, are titrations. A titration, the whole idea of a titration is you have like a unknown solution that has unknown concentration. What you're going to do is that you're going to react it with a solution that you do know the concentration of until these two molecules cancel each other out, and then calculate what the concentration of your unknown is. So let me try saying that again to make it make a little more sense. All right, let's say I gave you this sample of acid, and I said, I don't know what the molarity of this acid is, and I'm paying you like 20 bucks an hour to work in my lab. So go and figure out what the molarity of this acid is. What you would do is that you would get a base, right? And this base would have a known molarity. That is, you know what the molarity of this base is. And what you would do is that you would add base. So add base. Measure how much you add. So measure volume added. And you're going to add base until all of the acid in the solution has been made into water. And how would you know all your acid has been made into water? You use an indicator, right? In lab, you're going to use the same indicator as shown here. This indicator turns pink once your solution is basic. So the idea is that you slowly add base until your solution becomes pink, because that means you have no more acid. And then you use solution stoichiometry to figure out what the concentration of your unknown acid is. All right, so that's titrations in a nutshell. Again, listen to me talk about titrations, I'm sure does not make that much sense. So hopefully doing example problems about titrations will make a little bit more sense. So let's do that. The base is not the indicator, and the base is not the unknown in this example. The base is what you're adding. I know the concentration of my base, and the indicator is a third solution that you add in. And you just add in a couple of drops. And the indicator just turns pink in this case when the pH is basic. There's other indicators that change different colors on different pHs. But the one we're going to use in lab, or you're going to use in lab, I'm not teaching lab this year, is it will turn pink at a pH of 8. I forget the exact name. It's phenol something. The name escapes me right now, but it's phenol something. The unknown could be an acid or it could be a base. It could be either or. In this example, I just did acid. There's no reason why your unknown could be a base though, and you add acid of known concentration. And although in lab you only do acid-base titrations, you can do titrations for non-acid bases as well. So this has other practical applications, but the easiest way to learn it is by acid and base because your solutions can change colors. So just keep that in mind. This, although we're teaching it as acid base, you can use it for other substances. Yes, phenyl phthalate. Yeah, thank you. I'll write that out because my brain not works so good right now. Okay. All right. So let's do this. What this problem does is, hold on, I know this is going to be shocking. It's going to combine what we just learned about how to combine an acid and a base. It's going to take what we learned either on Monday or Wednesday, I forget now, in solution stoichiometry. And we're going to figure out molarities of our unknown here. Okay, I'm going to do A. So in any word problem, it behooves you to pull out the information that is most relevant to the problem. Yeah, there are a lot of different indicators out there, but in Gen Chem, we always use the pink one, phenolphthalein. Yeah, so let's do our problem here. I have so I have H2SO4. I have 30 mils of this, but it's unknown the molarity. So my molarity is a question mark, right? It takes me 25.23 mils of 0.150 molar NaOH. So I have NaOH, 25.23 mils. That is 0.150 molar. Remember, big M equals moles divided by liters. What's the molarity of H2SO4? So again, question mark. So what I did just there is something that I hope everybody can master going through this class. Looking at a word problem and just getting the relevant information, because now I can just ignore all the words. All right, strategy. First, write down your balanced equation. So I need a balanced equation. That's your first step, step one. So H2SO4 aqueous plus NaOH aqueous makes water liquid plus Na2SO4 aqueous. And I need to balance it. So if I go here and here, that should be balanced. Again, I don't expect anyone to balance nearly as fast as I can, so I know it'll take you a little bit more time to balance it, but that should be your balance equation. I'll just tell you the trick how I did it so fast, though. Na2, Na1, so I know that that Na has to become a 2 as well. So I put the 2 in front of there, and then I just scan with my eyes. I have 4 hydrogens, 2 hydrogens. Okay, I know a 2 has to go there. Now we have 4 hydrogens. And I just counted the oxygens in my mind super quick as well, and those balance out. So that's the quick way to do it. All right, so there's my balance equation. Now I need to do a giant conversion. I'm converting from mils of sodium hydroxide to get to molarity of H2SO4. So mils of NaOH to get molarity of HCl, right? So let's just start with mils of NaOH because that's what I need to start with. 2,3 ml NaOH, all right? Now, eventually I'm going to HCl. I know that, that's what my answer has to be in. So to convert between any two molecules, who can tell me Now, I'm not going to give you the answer straight away. Who can tell me what unit you have to be in to convert between two different molecules in a chemical equation? If I want to convert between NaOH to HCl, what is the only unit I can be in to make that happen? Moles. Yes, very good, everybody. I need to be in moles. So I know I'm going to moles, right? Now, right now I start in a volume. What unit tells me how to convert between a volume and the number of moles of a substance? What is that unit called again? It's not G. It's not grams. It's not liters. What I'm saying is that I start with a volume. There's some unit that'll tell me the relationship between moles and volume. It's not molecular weight. That's grams per moles. What in solution chemistry? So grams divided by milliliters is a density. What is that symbol? It's not density, that's grams divided by milliliters. So we could use, well, let me say, we could use density, but we don't have the density here. I don't give you density. So it's not M1V1 equals M2V2. That's a dilution equation. We're not diluting anything. A's number, it's not a number from the periodic table. Okay, look at this data. Look at all the variables I wrote out for you. It's not Avogadro's number. Avogadro's is how to convert between moles and atoms. So I gave you everything you need to know to solve this problem in the problem itself, right? And so you were correct. I need to be in moles of NaOH to get the moles of HCl. Right now I started on volume. What in this problem will allow us to convert between a volume and the number of moles of NaOH? You would use the moles of the, I don't know what an eton is, equation. That's stoichiometry. So we would use moles of the equation once we were converting between NaOH and H2SO4. We're not there yet. Molarity. There it is. I even wrote it right here. So this is a good refresher. I'm glad I asked that. Molarity tells you how many moles are in 1 liter of substance. So I would definitely write that down because that's a big concept. Molarity, big M, tells you how many moles are in a volume. So if I start with a volume and I know I need to go to moles, the way to convert between a volume and moles is molarity. And I'm given a molarity. Now, the only issue here is that my volume is in milliliters, molarity is in liters. So I need to convert between milliliters and liters. Oops, that's NaOH. And when we do that, there are 1,000 milliliters in 1 liter. Milliliters cancel out. Now I'm in liters of NaOH. Once I'm in liters of something, if I know the molarity, I can convert into moles because the molarity says for every 1 liter of NaOH I have, that is 0.150 moles, right? That's molarity, moles divided by liters, and that's moles of NaOH. So I've reached my goal. I know the moles of HCl. Or sorry, the moles of NaOH. And I don't know why I wrote HCl. That's H2SO4. Now that I'm in moles of NaOH, I can convert between any substance in my equation. And I do that by using stoichiometry. That is 0.150. Can we go directly to mole from milliliter? You can. Yes, you can. You can do, so just an aside, you can go 25.23 milliliter is 1,000 milliliter for 0.150 mole. Yeah, you could do that. There's no problem with that. But I'm just showing you the long way. Okay, so once we're in moles of NaOH, I can go to moles of H2SO4 from my equation. My equation says for every 2 moles of NaOH I have, that's 1 mole of H2SO4, right? So I can solve for that, and my unit, and this is why I love the train tracks, my units all cancel out. I'm left in a unit of H2SO4. I'm left in moles of H2SO4, which means I probably did my conversion right. So when you do this, you find out, okay, in my solution, if I did all my math right, I have 0.001892 moles. Again, take everything on the top, multiply together, divided by everything on the bottom. However, my answer, if we go back to the top, I want molarity, not moles. Molarity is moles divided by volume. My volume of H2SO4 was 0.030 liters. Well, actually 0.0300 liters. That's 30 milliliters. I did the conversion. And what you get when you divide those two are 0.0631 molar. So that's the answer. That's combining acid and base chemistry, which we worked on today, and solution stoichiometry, which we worked on earlier this week. So any questions about what I did there? Where did I lose you? What step? So if you think it'll take forever to solve it, the best way of getting quicker at it is to do practice problems. Like if you do 10 practice problems, all these are done the same way. So what I will do, I guess I'm going to start doing this since I have been getting people emailing me, and I appreciate that. I will probably start looking for problems on the internet and put links to that. So I will take like a couple minutes out of my day, look for good example internet problems, and ideally they'll have the answers right there, and I'll put those up as additional practice. Yeah, because these problems are all over the internet. And I'll put them up so you can trust they have been verified by me as good example problems, because I know one of the issues I usually hear from students when I ask them to go look on the internet for problems is that you're generally worried if they're good practice, they're teaching you something bad or not. So you'll have my Dr. Andrews seal of approval stamped right on there. So since we did not get to the lesson for today, will we go over it on Monday and everything shifts again? Yes, I was going to get to that. Today, the plan was to talk about redox reactions. We did not get to that. So what that means is that we will not have a reading guide due on Monday. You will not have a quiz due on Monday. So we're just going to push everything back a day. Again, that does not affect tests. It won't affect the test date. It's just going to be all my folders get pushed back a day. That might not happen till Sunday. I have a busy weekend ahead of me, but I'll try to get it done today, but it might not happen till Sunday. I'll put the links on Blackboard. I'll make an announcement about that. For the homework, I was confused on the assignment. If you're confused about the homework, please email me because I don't remember the problems off the top of my head. So quick question for the redox reaction, do they have both oxidation and reducing? Yes, they will always have oxidation and reducing agents. Will we have Pearson assignments for today? Yes, I will put a homework up for what we covered today. Yeah, that's why I put up homework only after we have done the lesson, because otherwise you would have homework on redox reactions because that was the plan and everybody would be confused. For B, what I will say for B is what I really want you to do is I want you to try and do that over the weekend to see if you can. See if you can read B and solve it for me. And if you get a solution and you want to know if it's the right solution, take a picture of it, send it to me, or just tell me what the final answer is. That works too, and I can say yes. If you get stuck, what I want you to do for B, and I implore you to do this, instead of just throwing up your hands and saying, I'm stuck, whatever, I don't care. I want you to take a picture of that work, whatever work you have, send it to me, and I can help guide you on that. So yeah, for B, that's going to be, I'm not going to grade it or anything, but I'm going to say, try to do that on your own. So for the redox reactions, yes, in a single reaction, you'll always have an oxidizing agent and a reducing agent. If you don't, then it wasn't a redox reaction. Yeah, you'll have 3 homework assignments due on Sunday. All right. After every single class, we have homework. Regardless if I shift things back or not, we'll still have homework. And we are out of time. So is there any other questions that you all might have? How do I know how to start the train track? Like I started with ML and A. Usually what I do is, how I do that is I want to start with my known. I hardly ever want to start with my unknown. So I want to start with my known quantities. And so you have 2 things to pick from. You have milliliters or molarity. And you can start with molarity. So if I did 0.150 moles of NaOH, and I get for 1 liter, and I convert that into milliliters, then you could go well, that's 25.23 milliliters of NaOH. Things cancel out. I'm left in moles of NaOH. Then you'd have a blank space here, which is okay. I just find that to be awkward if it's in the middle of the train tracks. So what I will try to do is I'll try to have a blank space at the very beginning. Generally for these problems, I kind of just know from intuition you want to start with volume. But definitely start with your known. And if you're doing solution stoichiometry, try starting with the volume of your known, if you're given that, or grams of the known, or moles of the known. That will help. Yeah. Unfortunately, that's one of the things that just comes from experience. And it's hard to articulate how I know that. Because in all honesty, either way does work. You can start with molarity. It'll work 100% the same way. Students just get confused. So I would just say start with the volume of the known. Have a good weekend yourself. Anything else? as I doodle. If not, I will put up a homework. I will put this online. You will not have a reading guide, so you're welcome. You will not have a quiz. You're welcome. I mean, I don't know why I'm saying you're welcome. I mean, it's all based on the speed of the class. All right. Other than that, take care, everybody. Have a good weekend.